Welcome back for another deep dive. You know we love to push the boundaries here. Today we're going deep into advanced mathematics, specifically this fascinating link between Bordism and resolving those tricky singularities. And you've given us quite the paper to unpack. Bordism and Resolution of Singularities by Mohammed Abouzaid and Shaoyun.
Yeah, this one is definitely a challenge. We're going to be talking about derived orbifolds. These are complex spaces that have symmetries built in. The paper looks at how to smooth out their singularities. Those are the points where the geometry gets a little strange.
I'm already intrigued. But before we get too lost in the complexities of derived orbifolds, can we start with something a bit simpler? Like, remind me about Bordism.
Absolutely. Bordism is a way of classifying geometric objects. You group them by whether they can be the boundary of something in a higher dimension. Picture a donut, a torus. You can imagine that as the boundary of a solid cylinder.
Yeah, like if you slice the cylinder right across its circular face.
Precisely. Now think about a sphere. Can you think of a three-dimensional object that has a sphere as its boundary?
Of course. A solid ball. Its surface is a sphere.
Exactly. So in Bordism, we would say the donut and the sphere belong to different classes because of their boundaries.
Okay, so we're grouping shapes based on whether they can be the edge of something in a higher dimension.
Yeah.
I get that. But why is that so important? What's the big deal with Bordism?
Well, it turns out that Bordism allows mathematicians to categorize and understand geometric objects in really deep ways, especially when you're working with spaces that have symmetries. It's a powerful tool.
Fascinating. And this paper uses Bordism to deal with the problem of resolving singularities, right? Those singularities are like wrinkles in the geometric spaces, right?
Yeah, that's a good way to put it. Singularities are those points where the geometry of a space breaks down. Think of the tip of a cone or where two lines intersect. These points can cause a lot of problems when you're trying to analyze these spaces.
I bet. So the goal of resolving singularities is to find a way to transform a space with singularities into a space without them, making it smooth.
That's exactly it. And what's interesting about this paper is that the authors tackle this problem for derived orbifolds, which are really tricky to work with.
Derived orbifolds sound a bit intimidating. Can you give me a simpler picture of what those spaces actually are? Something more concrete than just spaces with symmetries?
Okay, imagine you're looking at a map of a city, just streets and buildings. That's like a regular manifold. Now imagine someone adds layers of information to that map. Traffic patterns, wind direction, population density, all sorts of things. That's kind of like a derived orbifold. It's the extra information encoded mathematically.
So those extra layers of information are what make it derived, and they're also what create the singularities we want to smooth out.
That's right. Mathematically, they're represented by a section of a vector bundle over the orbifold, and they can introduce twists and turns into the geometry, leading to singular points.
I see. So the authors are trying to find a way to smooth out those twists and turns without losing the information encoded in those extra layers.
Exactly. It's a delicate process, and they use some really clever techniques to achieve it. Things like a three-step process for resolving singularities, Bordism, and special tools like normal complex structures and FOP sections.
Wow, this is already getting pretty complex, but I'm ready to delve into the specifics. Let's start with this equivariant stable homotopy theory. What does that even mean?
Well, it's all about understanding spaces that have symmetries, and it uses homotopy theory and Bordism to do that. Essentially, it's about studying geometric objects and their symmetries.
Okay, so we're not just looking at the shape of an object, but also its symmetry and how it affects things. How does this connect to resolving singularities?
A key result of the paper is a splitting of certain objects called homology theories. These are algebraic structures that capture information about the shape of a space. The authors find a way to decompose these homology theories into simpler pieces.
Split them, like divide them up.
Exactly. And this splitting applies specifically to maps between different Bordism theories, including ones that deal with symmetries.
So they're breaking complex mathematical objects into simpler parts while preserving information about their symmetries. I can see how this could be useful.
And this result has some interesting connections to other areas of math, like the evenness conjecture. This conjecture deals with the dimensions of certain geometric objects, and the paper suggests that their splitting result could shed light on its validity.
That's pretty cool. So they're not just resolving singularities, they're uncovering links between different areas of math. It's like they're putting together a giant puzzle.
Exactly. Now, are you ready to move into a realm that's fascinated both mathematicians and physicists? Gromov-Witten theory.
I've heard whispers of this theory. is about counting curves in abstract spaces, right? Something about pseudo-holomorphic curves and symplectic manifolds.
You got it. Gromov-Witten theory is all about counting those special curves in spaces called symplectic manifolds. These spaces are really important in physics, like in mechanics and string theory.
Oh, wow, we're getting into physics now.
Yeah.
Well, what does this paper have to say about it?
Well, mathematicians have been trying to define Gromov-Witten invariants, the things we count, in terms of cobordism for a long time. This paper makes a big step towards that goal.
Okay, this sounds important. What did they find?
There's a really exciting result in the paper, Theorem 1.13. It proves that there is a complex cobordism class associated with the spaces where we count those curves, the moduli spaces. This is a game changer because it allows us to extract real geometric information from these potentially messy spaces.
So they're connecting the abstract world of moduli spaces to the more concrete world of complex geometry. This Theorem 1.13 sounds crucial.
It is. It's like a translation tool between abstract algebra and geometry. They achieve this by using the concept of normal complex derived orbifolds and something called global Kuranishi charts.
I'm starting to grasp the depth of their work. Now let's get back to those derived orbifolds. Can you explain them in a bit more detail?
Sure. Remember, an orbifold is a space that locally looks like a quotient of Euclidean space by some finite group action. Think of a mirror reflecting part of a room. That exhibits local symmetry along the plane of the mirror.
Right, I get that. So how do we get from this simple picture to the idea of a derived orbifold?
In simple terms, a derived orbifold is defined by adding extra information to an ordinary orbifold encoded by a section of a vector bundle over that orbifold.
So it's those extra layers of information that make it derived.
Precisely. And they often introduce singularities into the orbifold. Theorem 1.20 in the paper links a derived orbifold Bordism group with an ordinary orbifold Bordism group. This connection helps simplify and understand the complex structure of derived orbifolds, getting us closer to resolving their singularities.
So they're using Bordism, which we talked about earlier, to tame the wildness of these derived orbifolds.
Yes. At the heart of their method is a three-step process for resolving singularities. Each step brings us closer to a smooth and well-behaved space.
Okay, let's hear about these steps. What's the first one?
The first step is called functorial embedded resolution. It uses an algorithm developed by Abramovich, Temkin, and Wlodarczyk to resolve the singularities of the zero locus of a section.
Zero locus. Can you remind me what that is?
It's essentially the set of points where that section, which holds the extra information, vanishes. It's often full of singularities. The first step smooths them out in a consistent way.
It sounds like they're pinpointing the problem areas and using a fancy math tool to fix them. What's functorial about it?
Functorial means it preserves important structural relationships as it smooths things out, like having precise instructions so you don't mess anything up.
What's the next step in this process?
It's called abelianization. The authors use a blow-up, a geometric transformation, to modify the orbifold. The goal is to make sure all the stabilizers of the resulting orbifold are abelian groups.
Wait, stabilizers. Abelian groups? I need a refresher.
Of course. Orbifolds have symmetry, right? The stabilizers describe that symmetry at each point. They tell us what transformations don't move that point. Like in our mirror example, the stabilizer of a point on the mirror would be the reflection itself. And abelian groups are groups where the order of operations doesn't matter, like addition.
Right, okay. So this step simplifies the symmetry structure of the orbifold, making it easier to deal with. How do they achieve this simplified symmetry?
With those blow-ups, imagine taking a point on a surface and replacing it with a whole line. That's essentially what a blow-up does. It changes the space's geometry in a controlled way. In this case, it helps simplify the symmetry.
Okay, so they're creating more space and order. What's the final step?
It's called deorbification. This is where we finally get a smooth manifold. They apply more blow-ups, carefully chosen to transform the orbifold into a smooth manifold without those pesky singularities.
So they start with a potentially singular derived orbifold, take these three steps, and end up with a smooth manifold ready for analysis.
You got it. The whole process relies on a key concept we mentioned earlier, normal complex structures. These are compatibility conditions on the complex structures of various bundles within the orbifold. They make sure the whole resolution process works properly.
Right, normal complex structures. It's like making sure all the parts of a machine fit together. Can you remind me what normal bundles are and why they're important here?
Sure. Normal bundles describe the directions that are perpendicular to the various layers of an orbifold. If you have a piece of paper folded in half, the crease is like a stratum. The normal bundle at a point on the crease describes directions perpendicular to that crease. A normal complex structure makes sure that the complex structures on these bundles are compatible, letting us do geometric transformations like those blow-ups without messing up the symmetry.
It's all about balance between geometry and symmetry. And the authors have figured out how to navigate this with their resolution process.
Exactly. To make this work, they introduce another idea, FOP sections. These are special sections of vector bundles over normally complex orbifolds. They're named after Fukaya, Ono, and Parker.
FOP sections. Sounds interesting. What makes them so special?
They have specific properties that make them work well with the author's techniques. For example, they have a normally complex lift that extends them to a bigger space in a way that's compatible with the orbifold's normal complex structure.
It's like those lifts allow them to build these sections in a way that fits the orbifold's geometry.
That's a good way to think about it.
Yeah.
The authors also prove some important properties of FOP sections, including regularity, which makes sure the resolution process is predictable.
Regularity again. Feels like a recurring theme, making sure things work as they should.
It is, and they show that regular FOP sections are open in a certain space of sections. This means if one is regular, nearby ones are too. It's important for making their process robust and reliable.
So they've created a robust toolkit for resolving singularities in these derived orbifolds. They're using a combination of Bordism, normal complex structures, FOP sections, and this careful three-step resolution process.
Yes.
Yeah.
And their work opens up possibilities for research in other areas of math, like symplectic geometry, homotopy theory, and algebraic geometry.
This is incredible. Now, I'm ready to get into the technical details. Can we start by looking at the definition of normally complex orbifolds in more depth?
Okay, let's dive into those normally complex orbifolds. We'll start with a smooth manifold, call it M, and a finite group acting on it. We'll call that O.
So M is our space and O represents the symmetries.
Precisely. Now, for any subgroup O within O, we have a fixed point locus Mo, which are the points in M that stay put under the action of O.
Like in our mirror example, the mirror plane would be the fixed point locus for the reflection.
Right. The normal bundle to this fixed point locus, NA, has a special structure called a O equivariant complex structure, denoted as IO. It lets us measure angles and orientations within the normal bundle, respecting the symmetry from A.
It's like a tailored coordinate system for the symmetry at each point.
That's a good way to think about it. Now, for the compatibility condition. For any two subgroups, O2 and 1, with IO inside EO, the embedding of NA into NO along ME1 must respect these complex structures.
So as we go from smaller to larger symmetry groups, the way we measure angles and orientations in the normal bundles needs to be consistent.
Precisely. This means the natural splitting of NA into NA2 and its orthogonal complement is preserved by the complex structures.
So the complex structures work well with how these bundles are embedded within each other. It's like making sure the symmetry structures fit together seamlessly.
Yes. Now let's move from a single manifold M to an orbifold U. Remember, orbifolds are locally like quotients of Euclidean space by finite groups.
Those local patches that capture the symmetry structure.
Exactly. To define a normal complex structure on an orbifold, we need two things. First, an atlas, a way to cover the orbifold with charts that look like those local quotients.
Like a patchwork quilt, with each patch having a symmetrical design.
Exactly. Each chart looks like UA, a space U acted upon by a finite group U. Second, each UA must have a normal complex structure, the kind we defined for manifolds, and they must be compatible.
Compatible. Yeah. Like the playing nicely condition for the normal bundles.
Right. This means when we look at the overlap of two charts, their normal complex structures must agree, like making sure the symmetrical designs on adjacent quilt patches match perfectly.
Okay, so a normal complex structure on an orbifold is about making sure the local symmetry structures fit together smoothly and consistently.
Exactly. With that, we can talk about normal complex structures on vector bundles over that orbifold.
Vector bundles, those families of vector spaces attached to each point, right?
Exactly. A normal complex structure on a vector bundle, E over U, means we can assign complex structures to the fibers of E in a way compatible with the normal complex structure on U.
Compatible again. So everything needs to fit together even when we're dealing with these extra layers of information from the vector bundle. Why is this important for what the authors are doing?
It's crucial for their resolution techniques because it allows them to perform geometric transformations, like blow-ups, in a controlled way, without messing up the symmetry of the orbifold.
It sounds like they've created a delicate balance, a set of rules for how to modify the space while preserving its symmetry. And this careful approach lets them transform messy orbifolds into smooth manifolds.
Precisely. To define those FOP sections, the authors use straightened metrics and connections.
Straightened metrics and connections. Those sound like ways to bring order to these spaces.
You could say that. They provide a framework for working with the geometry of orbifolds and vector bundles in a way that's suitable for the author's techniques.
I'm intrigued. Let's start with straightened metrics. What are they?
Imagine a manifold M. A straightened metric on M is a Riemannian metric that satisfies compatibility conditions with the group action. Specifically, for any subgroup M in M, the metric has to be straightened along Mo.
Straightened, what does that mean here?
It means the metric behaves predictably near Mo. It needs to respect how NM is embedded into TM along Mo.
So the metric doesn't cause any unwanted distortions or twists near Mo. It blends smoothly with the symmetry.
Yes, straightened connections are similar, but for vector bundles instead of manifolds.
Connections. They tell us how to transport vectors along paths, right? Like rules for how those little direction arrows change as you move from point to point.
Exactly. A straightened connection on a vector bundle over a normally complex orbifold makes sure the connection respects the normal complex structure of the orbifold and how it works with the normal bundles.
Compatibility and consistency again. Everything has to fit just right. And these straightened metrics and connections set the stage for defining FOP sections.
Exactly. The precise definition is technical, but FOP sections are sections of vector bundles over normally complex orbifolds that have a special kind of lift called a normally complex lift.
A normally complex lift. What is that?
In essence, it allows us to extend the section to a larger space, the normal bundle of the fixed point locus, in a way compatible with the normal complex structure.
So it's like taking the section and stretching it in a specific way, guided by the normal complex structure to make sure it fits in this larger space.
That's a good way to visualize it. And the authors prove some important things about FOP sections, like their openness and stability. These properties are important in their resolution algorithm, making sure the process works well and produces the desired smooth manifold.
It's amazing how much precision goes into designing this. They're building a very specific mathematical machine with each part carefully designed to play its role.
It really shows the power of mathematical thinking. Now, are you ready to see how they use this to tackle the resolution of those universal zero loci?
Absolutely. Those capture the essence of polynomial maps with symmetry, right? I'm ready to see how they smooth those out. All right, let's talk about these universal zero loci. They're like blueprints for the vanishing points of symmetrical polynomial maps, right?
Exactly. For a finite group of bow and complex O representations V and W, the universal zero locus ZE, VEW, captures the zero sets of equivariant polynomial maps from V to W of degree at most deed.
And the authors focus on a specific part of it, the smooth part, Z, VW. Why is this smooth part so important?
The smooth part has points with trivial stabilizers. This means those points aren't fixed by any non-identity element of O. Basically, the symmetry is well behaved there.
Interesting. So they're looking at the parts where the symmetry is less restrictive. What do they do with this smooth part?
They use the Abramovich-Temkin-Loderchik functorial embedded resolution of singularities algorithm.
That's a mouthful. What does that algorithm do?
It's a fancy way of saying it transforms a potentially singular algebraic variety into a smooth one using blowups.
Ugh, those blow-ups again. Always smoothing things out.
They're very useful for this. The functorial part means the resolution process keeps important structural relationships intact.
So they apply this algorithm to ZOD VWA. What do they get?
They get a smooth variety denoted as ZE VWW, which is the basis for their resolution process. Then they extend this to other parts of the universal zero locus with specific isotropy groups, focusing on points fixed by certain subgroups of B.
So they're tackling different levels of symmetry, smoothing things out at each level, and then they piece it all together.
Exactly. They resolve the singularities locally and then combine those local resolutions into a global solution.
Clever. It's like a jigsaw puzzle, smoothing the edges of each piece before fitting them together. You mentioned smooth bundles of algebraic varieties earlier. Can you explain those a bit more?
Sure. Imagine you have a smooth manifold, like a tabletop. On top of it, you have a collection of algebraic varieties, like vases. A smooth bundle of algebraic varieties is a smooth family of those varieties, parameterized by the points on the manifold.
Like a collection of vases arranged on a table. Each vase is an algebraic variety.
Exactly. The authors construct these bundles where the vases are those resolved universal zero loci we discussed.
Why construct these bundles?
They're key for their perturbation resolution algorithm, which connects derived orbifolds and ordinary orbifolds.
Perturbation resolution algorithm. Sounds like shaking things up to make those singularities disappear.
You could say that. The perturbation part is about slightly modifying the section of a derived orbifold to make it regular.
Regularity strikes again, making sure everything works as it should.
It's important for ensuring the resolution process goes smoothly. By choosing these perturbations carefully and using the properties of those smooth bundles, they can transform derived orbifolds into ordinary orbifolds, resolving the singularities along the way.
They're combining subtle modifications with advanced resolution techniques. What does all of this mean for other areas of math?
Their work has big implications for things like symplectic geometry and equivariant stable homotopy theory. In symplectic geometry, it offers new insights into moduli spaces of pseudo-holomorphic curves, which are important in Gromov-Witten theory.
It sounds like they're giving us a better way to look at those spaces. What about equivariant stable homotopy theory?
Their results lead to a splitting of certain homology theories. This gives us a deeper understanding of spaces with symmetries, particularly for maps between those Bordism theories that deal with symmetries.
It's amazing how their work ties together these different areas of mathematics.
It shows how interconnected math really is.
This has been an amazing deep dive. We've explored Bordism, orbifolds, resolution of singularities, and much more. We've seen how the authors smooth out those complex mathematical objects and how their work impacts various fields.
Their work shows how mathematical innovation can help us understand the universe better and lead to new discoveries.
To our listeners, we encourage you to dive deeper into this paper and explore its intricacies. The world of mathematics is full of amazing things waiting to be found.
Keep exploring, keep questioning, and keep pushing the boundaries of mathematical knowledge.
Until next time. Welcome to another deep dive, and this time we're tackling Bordism and resolution of singularities with applications to Gromov-Witten theory.
Oh, this is a good one.
It is, and with you being such an expert on proof, I think you'll appreciate just how elegant Abouzaid and Bai's work is.
Well, let's not forget about symplectic topology.
Right, we can't forget about that. That's a huge component of their work. We're going to see how they connect these seemingly very different concepts.
Seemingly different, yes.
Yeah, to achieve some really groundbreaking results.
We'll see how they clarify these really complicated Gromov-Witten invariants.
We will.
And even resolving singularities, which, as you know, can be a real headache.
Yeah, absolutely. So why don't we just jump right in and start with equivariant stable homotopy theory.
Okay.
Can you give us like a brief overview of what that even is?
So equivariant stable homotopy theory basically deals with topological spaces that have symmetries. So think of a sphere, you can rotate a sphere,
Okay.
and it looks the same. And this paper, in particular, is focusing on an equivariant homology theory that's built from this idea of Bordism.
Right.
And Bordism is where we look at these geometric objects and classify them based on their boundaries.
So we're not just looking at like an object in and of itself.
Right.
We're looking at, okay, what can it be bounded by?
Yes.
And how do those boundaries relate to the object itself?
Yes, exactly. And so, you know, the paper delves deep into the structure of what we call equivariant Bordism groups. These are sets of objects, these boundary-related objects that also have symmetries.
So we're adding this extra layer of complexity with the symmetries?
Yeah. Okay. Now, one of the key pieces here is Theorem 1.6, which really elegantly shows a connection between geometric Bordism and homotopical Bordism.
And these are like two very different theories, at least on the surface.
On the surface, yeah. They seem very different.
So can you unpack that a little bit for us?
So Theorem 1.6 basically says if this thing called the evenness conjecture fails for geometric Bordism, then it also must fail for homotopical Bordism.
Okay.
And so that connection kind of gives us these really valuable tools for understanding how these Bordism groups are structured and how they relate to each other.
So it's this interconnectedness that I think is so beautiful about mathematics.
Absolutely.
But it also makes it a little bit difficult to grasp sometimes.
Yeah.
Because there are all these moving parts.
Yeah.
Now, let's switch gears a little bit and talk about Gromov-Witten invariants,
Okay.
which I have to admit I always struggle with a little bit. They can be very difficult to work with. How does this paper help make them more manageable?
So Gromov-Witten invariants, just to refresh, they're tools for counting these special geometric structures within spaces called symplectic manifolds.
Right.
And they're really hard to define because the spaces we're dealing with, the moduli spaces of stable maps, they often have singularities and non-trivial symmetries.
So it's almost like we're trying to count things that are constantly in flux.
It's like trying to nail jelly to a wall.
Yeah.
It's a mess. But what Abouzaid and Bai do is they take a completely new approach using this concept of complex cobordism.
Okay.
Which, think of it as a new, more powerful way to measure and analyze these spaces.
Okay. So almost like we're changing our perspective a little bit.
Exactly. And this leads to Theorem 1.13, which is one of their landmark results. They established that there exists this complex cobordism class that's specifically associated with these often very troublesome moduli spaces.
So it's almost like they found a way to tame these wild spaces.
In a way, yes. And this lets them define Gromov-Witten invariants for any closed symplectic manifold.
That's impressive.
Which is huge.
Okay.
And this result's really interesting when you compare it to what's known as Coates-Giventoll's rational quantum cobordisms.
Okay.
That approach gives you a rational perspective, but Abouzaid and Bai are giving us an integral perspective, which is it's much more refined.
So we're getting a finer-grained view of the geometry.
Exactly.
So we've talked about complex cobordism.
Right.
We've talked about Gromov-Witten invariants. But where does the resolution of singularities fit into all of this?
So resolution of singularities is really at the heart of their approach.
Okay.
They have this this method for converting these complicated geometric objects called derived orbifolds.
Okay.
Into much nicer, much more well-behaved objects called stably complex manifolds.
So it's like we're taking something that's all knotted up and tangled.
Yeah.
We're trying to smooth it out.
Or untangling it.
Yeah. And they do this through a three-step process, right?
Yes.
Can you give us just a high-level overview of what those 3 steps are?
So the first step is they use this technique called functorial embedded resolution of singularities.
That's a mouthful.
It is a mouthful, but essentially it's this fancy algorithm from algebraic geometry that lets us systematically smooth out the rough parts of the derived orbifold.
So we're borrowing tools from another area of mathematics to help us here.
Exactly, and it's really elegant.
Yeah.
The second step is all about abelianizing the orbifold. Now, orbifolds have these symmetries represented by groups.
Right.
And abelianizing basically means simplifying these group actions, making them more commutative.
Okay.
So we're simplifying not just the geometry, but also the algebra behind it.
Yeah. So we're simplifying on multiple levels here.
Yes, exactly. And then finally, the third step focuses on resolving the remaining singularities in what we call the coarse space of the orbifold. So this is sort of like a simplified, a less structured version of the orbifold, and resolving its singularities is that final step towards getting a smooth space, a manifold.
So essentially they're taking this very complicated object and they're smoothing it out step by step.
Step by step.
Until they have something that's much more manageable to work with.
Exactly.
Okay. Well, that's a great overview. I think a good place to stop for part 1. I'm definitely eager to dig into the specifics of these 3 steps, and I know our listeners are too.
Oh, yeah, me too.
So we'll pick up there in part 2.
Sounds good. All right. So let's jump into section 7. This is where they introduce these regular FOP sections.
Okay, FOP sections. I remember those being a bit of a head scratcher when I first encountered them.
Yeah, they can be a little tricky.
They're named after Fukaya, Ono, and Parker, right?
That's right, yeah.
And they're essentially special types of sections of vector bundles over orbifolds. But what makes them so special for resolving singularities?
So think of it this way. We're trying to smooth out these rough edges in our orbifold.
Right.
And regular FOP sections give us a way to control that smoothing process to make sure the singularities either become smooth points or take on a specific type of singularity that we can handle more easily.
So it's like having a set of tools, each designed to address a particular type of singularity.
Exactly, yeah. And the key here is this notion of regularity. The authors define what it means for a FOP section to be regular, and they show that regularity is an open condition. So if a section is regular at a point, it's also regular in a small neighborhood around that point.
Okay, so that ensures that our smoothing process is kind of stable and well-defined.
Exactly. Yeah. Now, how do we actually find these regular FOP sections?
Yeah, this is a good question.
Well, this is where the universal zero loci come back into play.
Oh, right. Those blueprints for polynomial equations that we talked about earlier.
Exactly. They show that by carefully choosing parameters within those universal zero loci, we can actually guarantee the existence of these regular FOP sections that are tailored to our specific needs.
So it's like searching through a massive library of geometric shapes and finding the perfect template to guide our smoothing process.
Yeah, that's a good way to think about it. And once we've found this ideal template, we can apply it locally to our orbifold, smoothing out those singularities one by one.
And of course, they prove that this procedure actually works.
Of course they do. They're very thorough.
They're not just going to wave their hands and say, trust us, it works.
No, 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 no. They give you all the detail.
Right. Now, all this work with FOP sections and universal zero loci culminates in a really important result presented in section 8. Can you tell us a bit about that?
Yeah, so this is their main result, splitting of the natural map from complex Bordism to the Bordism theory of complex derived orbifolds.
Oh, okay, so this is the big payoff for all their hard work.
Yeah, this is the jewel in the crown.
But it also sounds a little bit abstract. Can you break it down for us? What does this splitting actually mean, and why is it so important?
So remember, complex Bordism is all about classifying objects based on their boundaries.
Right.
And complex derived orbifolds are those intricate spaces with singularities that we've been working so hard to resolve.
Right. Lots of rough edges.
Lots of rough edges, exactly.
Mm-hmm.
Now, there's a natural map between these two worlds, between these two Bordism theories. Okay. That basically takes a smooth object and sends it to its derived counterpart, which kind of encapsulates information about its potential singularities.
So it's like taking a perfectly smooth sphere and then considering all the different ways you could, poke holes in it or create creases or folds.
Exactly, yeah. Like creating a collection of crumpled up versions of the sphere.
Okay, I see. So what the authors prove is that this map can be split, which means we can go backwards.
Right.
We can start with the derived orbifold and recover a smooth object that represents it in a way that preserves all the essential information.
Exactly. We can go from the crumpled up sphere back to the smooth sphere without losing any of the key information about how it was crumpled.
So we have a two-way street between these two worlds, between the smooth and the singular.
Exactly.
That's amazing.
And that's incredibly powerful because it bridges this gap between these two seemingly very different domains. It allows us to transfer knowledge and insights between them.
So it's like having this dictionary that allows us to translate between the language of smooth spaces and the language of singular spaces.
Yeah, that's a great analogy.
That's really cool.
And this splitting has implications for all sorts of areas of mathematics, equivariant stable homotopy theory, obviously, but also symplectic topology, global homotopy theory. It's really far-reaching.
Wow. So they've really created a powerful tool here. They
have, yeah. And they don't stop there. In section 9, they show how to actually apply these results. They use them to define these complex Bordism-valued Gromov-Witten invariants, which are, a much more refined way to count those geometric structures we were talking about earlier.
So they're taking this very abstract machinery and they're showing how it can be used to solve concrete problems.
Exactly, yeah. And they give a specific example of how these invariants can be applied to the study of Hamiltonian fibrations over the sphere.
Okay, so a very specific problem in symplectic topology.
Right.
That's fascinating. I'm really starting to see how all these pieces fit together.
It's a beautiful tapestry.
Now, I'm really eager to dig into the details of their three-step resolution process. This is the heart of their approach, right?
Absolutely. This is where the magic happens.
So let's jump into section 3, where they lay the groundwork for their approach to resolving singularities in these normally complex orbifolds.
Right. So this is where we encounter this concept of abelianization, which, as we mentioned before, is about simplifying the symmetries of the orbifold. Yeah. And they achieve this using this technique called blow-up, which is it's a powerful tool from algebraic geometry.
Okay, blow-ups. They sound a bit dramatic.
They are, in a way. Imagine you have a surface with a singular point, like a sharp corner. A blow-up essentially replaces that point with an entire copy of a projective space.
Okay, so it's like inflating a tiny balloon at that point, and as the balloon inflates, it kind of smooths out the sharp corner.
Exactly, yeah. And by doing this strategically, we can modify the group actions on the orbifold, making them more abelian, which essentially means that the group operations become more commutative.
Okay, so it's like we're taking these complicated group actions and turning them into something more like simple addition.
Exactly. Now, to keep track of all these blowups, they introduced this concept of a normally complex pair, which consists of a normally complex orbifold and a collection of divisors.
Okay, divisors. Those are hypersurfaces, right?
Yes, that's right.
And they kind of act like breadcrumbs, marking the spots where we've performed blowups.
Exactly. They give us a record of the transformations we've performed on the orbifold.
Okay, so we're not just blowing things up randomly, we're doing it in a very controlled way.
Very controlled, yes. And using these divisors, they define this invariant called the age of a point, which basically tells us how far a point is from being smooth. And they target points with the highest age, performing blowups to reduce the complexity of the orbifold.
It's like they're strategically targeting the most problematic areas and smoothing them out one by one.
That's a good way to put it. And of course, they prove that this process actually terminates. We don't end up in an infinite loop of blowups.
That's good to know. Otherwise, we'd be blowing things up forever.
Exactly. So at the end of this process, we're left with a normally complex pair that's ready for the next stage of the resolution.
Okay. So what's next? Where do we go from here?
So in section 4, they move on to resolving the singularities of the coarse space of our newly abelianized orbifold.
The coarse space, that's like a simplified version of the orbifold, right?
Yeah, think of it as a blueprint of the orbifold without all the fine details.
Yeah.
And smoothing out its singularities is crucial for constructing our smooth manifold.
Okay, so it's like we've zoomed out a bit.
Exactly.
We're
Yeah.
looking at the big picture now.
And they have another 3-step process for this.
Another 3-step process.
They-
They really like their 3-step processes.
They do, yeah. It's a good way to break down a complex problem.
Makes it more manageable.
Exactly. So the first step here is called divisorial alification.
Divisory alification. That sounds a little bit intimidating.
It does, but it's not as bad as it sounds. Essentially what we're doing is we're manipulating the orbifold to make sure that the singularities are well behaved with respect to the divisors, those breadcrumbs we placed earlier.
Okay, so those breadcrumbs are more than just navigational aids.
They're crucial for controlling the singularities.
I see. And how do they achieve this divisorial alification?
Well, again, it comes down to blowups. They introduce this concept of divisorial index, which tells us how far a point is from being divisorial, meaning its singularity lies entirely within a divisor, and they strategically blow up along loci where this index is maximal.
Okay, so we're kind of herding the singularities towards the breadcrumbs.
That's a good analogy, yeah. And by doing this, we simplify the geometry significantly, and again, they prove that this process terminates after a finite number of steps.
Okay, good. So we're not going to be blowing things up forever.
No, we have an endpoint in sight.
And once we've achieved divisorialification, what's next?
The next step is toroidalization.
Toroidalization. That sounds even more intimidating than divisorialification.
It does sound a bit scary, I know. But essentially what we're doing is we're transforming the orbifold to make sure that the singularities locally look like these things called toric varieties.
Toric varieties, what are those?
So toric varieties are spaces with a very specific geometric structure that's related to lattices and cones.
Lattices and cones. That sounds like linear algebra.
It is, yeah. And it turns out that toric varieties have a very deep connection to linear algebra, and the authors exploit this connection to further simplify the singularities. They introduce this concept of toroidal index, which tells us how far a point is from being toroidal, meaning it locally looks like a toric variety. And just like with divisorialification, they strategically blow up along loci where this index is maximal.
So we're kind of imposing this toric structure onto the singularities, guiding them into a more manageable configuration.
And as you might expect, they prove that this process also terminates.
Okay, good. We're making progress. So now we've got this normally complex pair that's been divisorialized and toroidalized. What's the final step?
So the final step is where it all comes together. We take our carefully prepared, normally complex pair, and we perform a final series of blowups to completely resolve the singularities of the coarse space.
This is the grand finale.
Exactly. And they do this by leveraging the fact that the singularities are now nicely organized with respect to both the divisors and the toric structures.
So all that careful preparation is really paying off now.
It is, yeah. And they prove that this final stage successfully resolves all the singularities, leaving us with a smooth manifold that's diffeomorphic to the original coarse space.
Wow. So we've gone from this complicated singular object to a smooth, well-behaved manifold.
And we've done it in a very controlled and systematic way.
This is incredible.
It's a beautiful result, and it's just the beginning. We still need to see how they use this to construct the Gromov-Witten invariants and apply them to specific problems.
I'm excited to see where they take it next. But I think we need to give our listeners a chance to process all this information.
Yeah, it's a lot to take in.
So we'll pick up the story in part 3.
All right, so picking up where we left off, let's dive into section 9. This is where they finally apply all this machinery to define those complex Bordism-valued Gromov-Witten invariants.
Yeah, this is where we see the rubber meet the road.
Exactly. So remember, Gromov-Witten invariants are tools for counting these certain geometric structures in symplectic manifolds.
Right, and they can be really difficult to define.
Yeah, they can be quite tricky. But what Abouzaid and Bai do is they use their resolution process to actually construct a complex cobordism class.
Okay.
That's specifically associated with these moduli spaces of stable maps.
Right, the spaces that encode all those geometric structures we're trying to count.
Exactly. So instead of just getting a number, like in the classical approach, we're now getting a much richer geometric object.
So we're seeing Gromov-Witten invariants through a new lens.
Precisely. And this gives us a much deeper understanding of their geometric meaning.
That's fascinating. Did they give any specific examples of how these complex Bordism-valued Gromov-Witten invariants can be applied?
They do, yeah. They look at Hamiltonian fibrations over the sphere,
Right.
which is this problem that's deeply connected to both symplectic geometry and dynamics.
Right.
And they show how their invariants can be used to analyze the structure of these fibrations.
So it's a very concrete application of their very abstract theory.
Yeah, it's a beautiful example of how this kind of abstract machinery can be used to solve real problems.
Well, I think that brings us to the end of our deep dive into the work of Abouzaid and Bai.
Yeah, I think so.
We've covered a lot of ground.
We have. We started with this very abstract idea of complex Bordism.
Right.
And then we saw how they developed this incredibly powerful machinery for resolving singularities.
Right.
And then finally, we saw how they applied all of this to define these new Gromov-Witten invariants.
And solve problems in symplectic topology.
Exactly.
It's really a remarkable piece of work.
It is, yeah. It's a testament to the power of abstract mathematical thinking.
Absolutely. To our listeners, we hope you've enjoyed this journey into the world of complex Bordism and resolution of singularities.
Yeah, and we encourage you to check out the paper yourself. There's so much more to explore.
There is. And who knows? Maybe you'll be inspired to make your own contributions to this exciting field.
That would be great.
Until next time, keep exploring the fascinating world of mathematics.
Keep those brains working.
Welcome back, everyone. Ready to dive into something pretty fascinating. Today, we're going to be exploring the world of complex Bordism.
Oh, yeah. It's a good one.
And we're going to see how it intersects with Gromov-Witten theory.
It's a very interesting area where topology meets geometry.
Yeah. And looking at this source material, it seems like we're going to be using some powerful mathematical tool.
Yeah, we'll need those to try to understand some really interesting geometric spaces.
Okay. So I guess the big idea here is to take these kind of complex objects, things like derived orbifolds.
Right.
And we want to use these techniques like resolution of singularities.
Resolution of singularities is going to come up a lot today.
Yeah, it sounds like it. Resolution of singularities to kind of make them more manageable.
Yeah, exactly. You can kind of think of it like taking this big tangled mess of mathematical yarn.
Oh, I like that.
And you're trying to carefully tease it apart.
Teasing it apart.
Yeah, and see the really beautiful structure underneath.
Okay, so I guess before we get too lost in the weeds here,
yeah,
can we take a step back?
Sure.
And just kind of like remind ourselves what Bordism actually means?
Bordism, the idea is you're grouping geometric shapes together based on their boundaries.
Okay.
And these shapes are manifolds. So you can say a coffee cup and a donut are in the same Bordism class.
Okay.
Because they both have one hole.
They both have one hole.
Right.
So how does this connect to Gromov-Witten theory?
Right.
Which is, as I recall, all about counting curves on spaces.
Right. Gromov-Witten theory usually lives in the world of rational numbers, but the research we're looking at today actually explores the idea of extending those invariants to complex Bordism.
To complex Bordism. Okay, so we're sort of upgrading
exactly
our counting system from something basic to something more sophisticated,
Yes.
more powerful.
Yeah.
Okay, and the connection between these two seemingly kind of different areas is built using this thing called equivariant stable homotopy theory.
Right.
Okay, that sounds a little intimidating.
Oh, it's not so bad.
Can we break it down?
So you have a square. You can rotate it 90 degrees, right?
Sure.
That's a group action.
Yeah.
So equivariant stable homotopy theory deals with spaces that have these kinds of symmetries.
Okay.
And we're trying to see how it all connects to Bordism.
So we're not just looking at the shapes, but we're also looking at their symmetries.
Exactly.
Okay.
Yeah.
So how does all of this tie back to this idea of resolving singularities?
So resolving singularities is basically smoothing out the rough edges of the geometric objects we're looking at.
Okay.
And the important thing here is by resolving singularities in this particular way, we can actually change these complex objects that have symmetries into simpler ones.
Okay.
And the key is we're not losing any information.
We're not losing any information, so it's like taking a rough diamond
Yes.
and carefully polishing it to reveal its brilliance.
That's a great analogy.
Okay.
And the research we're looking at today goes into detail about this three-step process for doing this. And the first step is called functorial embedded resolution of singularities.
Functorial embedded resolution. That's a mouthful.
Yeah, it is.
What does that actually mean?
So what you're going to do is you're going to use an algorithm called the Abramovich-Temkin-Lodarsik algorithm to smooth out the singularities of a geometric space.
So we're not just like blindly smoothing things out.
Right.
There's a purpose behind it.
Yes. And you're doing it in a very specific way so that you can preserve these really important properties.
Okay.
You could think of it like you're using this really high-tech sanding tool.
Okay.
That's not only smoothing out the surface, but also maintaining the integrity of whatever you're working with.
So what about the other steps in this process?
So the next step is called abelianization.
Abelianization.
And what that's going to try to do is to simplify the group actions that are involved.
Simplify.
Yeah, you can almost think of it like taking a complex musical score and rearranging it for a smaller ensemble. So the melody is still there, but it's just a little bit easier to grasp.
To grasp. I see. So each step is sort of building on the previous one.
Exactly.
To gradually simplify this object.
Right.
But we want to keep its core characteristics.
Exactly. And the final step is to trivialize the remaining stabilizers.
Okay.
And you can think of this like taking a pattern fabric.
Okay.
And you're going to merge similar patterns to try to create this uniform texture.
Okay. So after all of these three steps, we've gone from something complex, maybe something jagged, to something smoother and simpler.
Right.
Okay. So why go through all of this trouble?
Right. So the beauty of this resolution process is it's not just a trick you can use one time. It's a technique that can be applied to lots of different mathematical situations.
So it's like having this master key
Yes.
that unlocks the secrets within different kinds of mathematical structures.
Yeah, and it comes up a lot in a lot of different areas.
But how does this all connect back to what we were talking about with Bordism and Gromov-Witten theory?
Right. So this is where it gets really interesting. The paper we're looking at talks about these things called regular FOP sections.
Regular FOP sections.
Yeah. And they're really important because they make sure that the spaces we're dealing with, particularly the ones in Gromov-Witten theory, are well behaved.
So we're not just smoothing things out to make it pretty.
Right.
We're doing it in a way that preserves the math.
Exactly.
Okay. That's clever. But before we get too far down this road, I think it's important to kind of reiterate why this matters.
Yeah.
What are the broader implications?
So one of the most exciting things about this research is it can really have an impact on how we understand complex systems in the real world. So think about modeling something like the stock market or trying to predict how a disease might spread.
These are really complex systems.
Yeah, I have so many variables.
It's like trying to solve a giant Sudoku puzzle in the dark.
Exactly. So what if we could use these resolution techniques to simplify those systems, but without getting rid of their important characteristics?
So we could actually see the underlying order within the chaos.
And this is just the beginning. The paper actually goes on to explore these applications of resolution techniques to specific areas like symplectic topology and the topology of spaces of Hamiltonian maps.
Oh, these deep dives.
Yeah.
You start with something really focused, and then you uncover this whole universe of math ideas. It's like you're pulling on a loose thread, and then the whole tapestry unravels.
Exactly. And our journey's just beginning. We've got a lot more to unpack with this deep dive. So let's explore a little further into this intersection of Bordism, Gromov-Witten theory, and this really neat idea of resolving singularities.
Sounds good. Let's do.
Okay, so now that we've kind of laid the groundwork, let's really get into the heart of this paper.
Okay.
How it actually uses resolution of singularities to connect complex Bordism and the Bordism theory of complex derived orbifolds.
Yeah, so this is where the real magic happens. It's like we're trying to create this way to translate between two mathematical languages.
You got it.
Like a secret decoder ring.
Yeah, like deciphering an ancient code.
Okay.
And the key to all of this is in Theorem 1.20.
Theorem 1.20.
Yeah.
Okay.
Which introduces something called a natural transformation.
A natural transformation.
Denoted by Z.
Z, okay.
And this Z is like the bridge between these two Bordism theories.
Okay, I'm intrigued, but I have to admit, whenever I hear natural transformation, I kind of get a little intimidated.
Yeah, I know it can be a little bit confusing.
Can you demystify it a bit?
Yeah, basically, a natural transformation is a way to map between two different mathematical structures. But you want to do this in a way that keeps all the important relationships the same.
Okay.
Like if you have a blueprint of a building and you make a 3D model from it, right?
Oh, okay.
The structure is the same, it's just represented differently.
So this Z transformation is taking information from those derived orbifolds.
Yeah.
Those really complex, maybe kind of rough-edged spaces, and translating it into the language of regular orbifolds.
Exactly.
Which are smoother and easier to work with.
Right. And what's really remarkable about Z is it actually splits the natural map.
Splits the map.
From the Bordism of manifolds to the derived orbifold Bordism.
Hold on. Splits the map. Can you elaborate on that?
Imagine a river that flows into a lake, right?
Okay.
The natural map is like the water flowing from the river to the lake.
Okay.
Now imagine you put a dam in that river.
Okay.
And it diverts some of that water back into a separate channel.
Okay.
That's what Z does.
Okay.
It creates this other pathway. Back from the derived orbifolds to the regular orbifolds.
So it was like a two-way street.
Exactly.
You can go back and forth
Yeah.
between these two mathematical worlds and carry information with us.
Exactly. And what this splitting tells us is all the information that's inside the derived orbifold Bordism can basically be captured by focusing on the regular orbifolds.
Thanks to Z.
Right. Thanks to Z.
That's pretty amazing. It's like we've found a shortcut through this dense forest of math.
Yeah, and it lets us explore Gromov-Witten theory in a whole new way.
Because we can use complex Bordism.
Exactly.
So we're not just counting curves anymore.
Right.
We're counting them in this way that incorporates this richer structure
Got it.
of complex Bordism.
Exactly. And this actually goes way beyond just counting curves.
Oh, wow.
So the paper highlights how these techniques can be used to study moduli spaces of pseudo-holomorphic curves, which are these really important objects in symplectic topology.
So this Z transformation can help us understand all sorts of geometric and topological problems.
Exactly. It shows how powerful math is. You can connect all these different areas and find hidden relationships.
But let's not get ahead of ourselves. You mentioned that Z is built using those three resolution techniques.
Yes.
Smoothing singularities, simplifying group actions, and trivializing stabilizers. Can we walk through that?
Yeah, so you have to carefully apply those techniques in a way that makes sure that Z really is a natural transformation.
So it's not just blindly applying them.
No. It's very precise, like surgery.
Okay.
You're reshaping it without breaking it.
Okay. The paper goes into a lot of detail about this construction.
It does.
I'm impressed. But before we get into all those details, I have a question.
Yeah.
You said the Z transformation is a natural transformation.
Right.
Does that mean it's unique? Or could there be other ways to split those Bordism theories?
That's a really good question.
Thanks.
And it points to some really important open questions. Theorem 1.4 tells us that there is a splitting.
Yeah.
But it doesn't say that Z is the only one.
Okay.
So it's possible that other natural transformations could achieve that same splitting.
So there's still a lot to explore.
Yeah, there's always more to discover in math.
Okay, well, for now, let's focus on the Z that's in the paper.
Right.
Because they did a great job outlining the steps and proving the key properties.
They did.
But can you remind us why this Z is so important?
Yeah.
Especially for Gromov-Witten theory.
So remember, Gromov-Witten invariants usually live in the rational numbers.
Right.
But what we're doing is extending those invariants to complex Bordism.
Which is a much richer structure.
Yes, much more nuanced.
So it's like upgrading our math toolkit to something much more powerful.
Exactly.
Okay.
And Z is the key.
Okay.
By applying Z to those derived orbifolds that represent moduli spaces of curves, we can translate the Gromov-Witten invariants into the language of complex Bordism.
Like a secret code.
Yes.
Embedded in these geometric spaces.
Exactly.
So what does this tell us? What new information can we get by doing this?
Well, for one thing, now we can ask about divisibility.
Divisibility.
Of these invariants within the complex Bordism ring, which we couldn't do with the rational numbers.
Because it's a richer structure.
Right. And we can also see relationships between these invariants that were hidden before.
So it's not just counting curves.
Right.
We're understanding their deeper relationships.
Yes. Okay.
Within this more intricate structure.
And this has implications for other areas, too.
It does. The paper talks about Hamiltonian fibrations.
Yeah.
And the topology of spaces of Hamiltonian maps.
It's amazing how this framework connects everything.
It is.
And unveils these hidden relationships. It's mind-boggling to think about how this could impact our understanding of complex systems in all kinds of fields, from physics to economics to biology.
Yeah, it really is.
So let's take a step back and think about what we've done. We talked about Bordism, derived orbifolds, the Z transformation.
Yeah.
It's been quite a journey.
It has.
And the journey's not over yet. We still have more to explore. Like, all of this connects to normally complex orbifolds.
Yeah, we're going to get to that. That's next.
So we've explored the Z transformation and how it bridges the gap between complex Bordism, derived orbifold Bordism.
Right.
But now I want to talk about a specific kind of geometric object.
That plays a big role in all of this. Normally complex orbifolds.
Yes, normally complex orbifolds. They're really important.
They're important for the resolution process, and they have these deep connections to symplectic topology.
Right, they come up everywhere.
You mentioned earlier that moduli spaces, which parameterize those curves in Gromov-Witten theory,
Right.
they're expected to have this normally complex structure.
Yes, that's right.
Can you unpack that a little?
Yeah, so this expectation comes from these automorphisms.
Automorphism.
Yeah, those symmetry transformations in the moduli spaces.
Okay.
And a lot of these automorphisms come from those closed, irreducible components of the curves domains.
Okay, remind me what automorphisms and domains mean again.
Okay, so think about drawing a curve on a rubber sheet.
Okay.
The rubber sheet is like the domain.
Okay.
It's where the curve lives.
Got it.
Now imagine stretching or twisting that sheet without changing the curve itself.
Okay.
Those are automorphisms.
Oh.
They're transformations that keep the shape of the curve, but they can change its position.
Gotcha. So they're like symmetries that are built into the curves.
Exactly. And when we look deeper, these automorphisms turn into these complex representations that come from the equivariant Fredholm indices of the linearized deformation operator.
Equivariant Fredholm indices and linearized deformation operator. Those sound like terms that could launch 1,000 spaceships.
Sorry, I got a little jargony there.
No worries. Can we simplify that a bit?
Okay, so the deformation operator is basically a tool that helps us understand how we can deform a curve.
Deform.
Yeah, like wiggle it around without it leaving the moduli space.
Okay.
It's like figuring out how much flexibility the curve has.
How much wiggle room?
Right. The linearized part means we're simplifying the operator so it's easier to analyze.
Okay.
And equivariant means we're considering those symmetries.
Those automorphisms.
Right, the automorphism.
So we're looking at how those curves can wiggle around.
Yeah.
But we have to respect their symmetries.
Exactly. Now, those complex representations come from analyzing that linearized equivariant deformation operator.
Okay.
And it turns out that this thing called the Fredholm index gives us these complex representations.
So it's like the deformation operator has this secret code.
Yes.
And that code is written in the language of complex representations.
That's a great way to put it. And since those representations come from the automorphisms of the curves,
which are mostly complex.
Right. The moduli spaces also inherit this normally complex structure.
So it's like the symmetries of the curves kind of imprint their complex nature on the bigger spaces.
Exactly. That's a great way to think about it. And the structure is really important because it lets us use those resolution techniques.
It's like the key
Yes.
that unlocks those powerful mathematical tools.
Right. And because moduli spaces usually have this structure, because of the automorphisms, we can use those 3 steps.
Functorial resolution.
Yes.
Abelianization.
Yeah.
Trivialization.
You got it.
To turn these moduli spaces into manifolds.
Right.
While keeping all the information.
Exactly. And this lets us understand Gromov-Witten invariants and symplectic topology in a whole new way. We can see new relationships and explore new structures.
And maybe even connect these ideas to real-world stuff.
Exactly. Imagine physicists studying subatomic particles. Their interactions are super complex, but we can use symplectic topology to describe them.
So symplectic topology is like a language for understanding particles.
Exactly. And just like Gromov-Witten theory, they use moduli spaces to look at the possible states of those particle interactions.
Okay.
So if they use these resolution techniques, they can simplify those moduli spaces.
And that could lead to new insights.
It could, about those fundamental forces that control the universe.
That's amazing. These abstract math concepts could help us unlock the mysteries of the cosmos.
Math is powerful like that. It connects the theoretical and the practical.
This deep dive has been quite a journey. From Bordism and Gromov-Witten theory to derived orbifolds and resolutions.
It has been.
It really shows how math can surprise us with connections and insights.
It's a beautiful thing.
It really is. So to wrap things up, I want to encourage everyone listening to stay curious about math. You never know what amazing things you might discover.
Right. There's always something new to learn.
So thanks for joining us on this intellectual adventure. Keep those minds engaged because the world of math is vast and fascinating.
It is.
Welcome to another deep dive. Today we're going to be looking at Bordism and resolution of singularities with applications to Gromov-Witten theory.
Wow. Yeah, that's a mouthful.
Yeah, it sounds like it's going to be pretty intense.
It is. It's a really fascinating paper, though.
So what is it about?
Well, it's about using techniques from algebraic geometry to solve problems in symplectic topology.
Okay. And what kind of problems?
One of the big ones is resolving singularities.
What does that mean?
It means taking a space that has some kind of jagged edge or a point or a cusp or something and smoothing it out.
Why is that important?
Well, it makes the space easier to work with mathematically, but it also has applications in other areas like physics.
Okay. So how does this paper go about resolving singularities?
It uses a really clever method called functorial embedded resolution.
Functorial embedded resolution.
Yeah. It's a way of resolving singularities in a way that preserves certain properties of the space.
Like what?
Like symmetry, for example.
Okay, that makes sense. And so this paper applies this method to symplectic topology.
Right. And one of the big applications is to Gromov-Witten theory.
Gromov-Witten theory. What's that?
It's a way of studying symplectic manifolds by counting certain kinds of curves on them.
Curves, like lines and circles.
Yeah, exactly. But they can be much more complicated than that.
I see. And how does resolving singularities help with that?
It makes it easier to count the curves because you don't have to worry about the singularities messing things up.
Okay, I think I'm starting to get the picture. So this paper is basically about using algebraic geometry to smooth out symplectic manifolds so that we can count curves on them more easily.
That's a pretty good summary.
Yeah. So what are some of the key results of the paper?
Well, one of the big ones is that it shows how to define Gromov-Witten invariants in terms of complex cobordism.
Complex cobordism. What's that?
It's a way of measuring the complexity of a space.
And why is that important?
Because it gives us a new way to understand Gromov-Witten invariants. And it also has implications for other areas of mathematics like homotopy theory.
Okay, so this paper is really making some big contributions to our understanding of symplectic topology.
It is. It's a really exciting piece of work.
Well, I'm definitely looking forward to learning more about it. So let's dive into the paper and see what we can uncover.
Sounds good to me.
Okay, so the paper starts by giving an overview of the problem of resolving singularities.
Right, and it explains why this problem is so important in symplectic topology.
And it also introduces the concept of functorial embedded resolution.
Yeah, and it explains how this method can be used to resolve singularities in a way that preserves certain properties of the space.
Like symmetry.
Exactly.
Okay, so now that we have a basic understanding of the problem and the method, Let's move on to the next section of the paper.
Okay, sounds good.
This section introduces the concept of a normally complex orbifold.
Right, which is a key concept in the paper.
So what is a normally complex orbifold?
Well, it's a space that has a certain kind of structure.
What kind of structure?
It's a bit technical, but basically it means that the space can be locally modeled on a complex manifold.
A complex manifold.
Yeah, a complex manifold is a space that can be described using complex numbers.
Ah, okay. So a normally complex orbifold is like a space that's built out of complex manifolds.
Sort of, yeah. It's a bit more complicated than that. But that's the basic idea.
Okay. And why are normally complex orbifolds important?
Well, they're important because they show up a lot in symplectic topology.
Like where?
Like in the study of Hamiltonian fibrations.
Hamiltonian fibrations.
Yeah, it's another technical term, but basically it's a way of describing the dynamics of a physical system.
I see. And so normally complex orbifolds are important for understanding these Hamiltonian fibrations.
Exactly.
Okay, so now that we know what a normally complex orbifold is, let's move on to the next section of the paper.
Okay. This section explains how to abelianize a normally complex orbifold.
Abelianize.
Yeah. It means to make the orbifold more commutative.
Commutative.
Yeah. It means that the order in which you do things doesn't matter.
So like if you're adding numbers, it doesn't matter if you add 2 plus 3 or 3 plus 2.
Exactly. And in the case of orbifolds, it means that the order in which you compose the charts doesn't matter.
Charts.
Yeah, charts are like the maps that you use to describe an orbifold.
Okay, so abelianizing orbifold means making it so that the order in which you compose the charts doesn't matter.
Right.
And why is that important?
Because it makes the orbifold easier to work with.
Okay, I think I understand. So this section of the paper explains how to abelianize a normally complex orbifold.
Exactly.
Okay, so now that we know how to abelianize an orbifold, let's move on to the next section of the paper.
All right. This section explains how to desingularize the coarse space of an orbifold.
Desingularize the coarse space.
Yeah, the coarse space of an orbifold is like a simplified version of the orbifold.
And desingularizing it means?
It means getting rid of the singularities.
Okay. So this section is about smoothing out the coarse space of an orbifold.
Exactly.
And why is that important?
Because it makes the orbifold easier to work with.
Okay, I think I'm starting to see a pattern here. Each section of this paper is about making the orbifold easier to work with in some way.
That's right.
Okay, so now that we know how to desingularize the coarse space of an orbifold, let's move on to the next section.
All right. This section explains how to construct a manifold from an orbifold.
A manifold from an orbifold.
Yeah, so remember that an orbifold is like a space with singularities.
Right.
And a manifold is like a space without singularities.
So this section is about taking an orbifold and smoothing it out so that it becomes a manifold.
Exact.
And why is that important?
Because manifolds are much easier to work with than orbifold.
Okay, I think I understand. So this section is about taking all of the techniques that we've learned so far and using them to construct a manifold from an orbifold.
Right.
And once we have a manifold, we can start doing all sorts of interesting things with it.
Exactly. We
Yeah.
can study its topology, its geometry, and its dynamics.
Wow. This is really fascinating stuff.
It is. It's amazing what you can do with mathematics.
I know. And I'm really enjoying learning about it with you.
Me too. This is a really fun deep dive.
It is. So where do we go from here?
Well, the next section of the paper starts to get into the applications of these techniques.
Applications. Like right.
Like to Gromov-Witten theory and Hamiltonian fibrations.
Cool. I'm looking forward to it.
Me too. It's going to be good.
All right, so we're back and ready to dig deeper into this paper. We left off talking about how to get a manifold from an orbifold. What comes next? Okay,
so the next section, section 6, is about this really powerful tool from algebraic geometry.
Hit me with it.
It's called the Abramovich-Temkin-Ledarzik functorial embedded resolution of singularities algorithm.
Okay, so not exactly a catchy name. What does it actually do?
It's all about resolving singularities.
Yeah.
But what makes it so special is that it's functorial.
Functorial, right. We touched on that before, but remind me what that means again.
It means that it works consistently with maps between spaces.
Gotcha. So you can use it to kind of patch together local resolutions and get a global one.
Exactly. And that's super helpful when you're dealing with complicated spaces.
Makes sense. Now, this section also mentions something called universal zero loci. What are those all about?
Think of them as model systems for studying singularities. They're algebraic varieties that capture the essence of the problem.
Okay, so it's like a simplified version that we can use to test out our tools.
Yeah, that's a good way to think about it. And the paper shows how this F infinity E R algorithm, as they call it, can be used to resolve the singularities of these universal zero loci and get smooth varieties.
So we're smoothing things out again. I see a pattern here.
Definitely. And these smooth varieties will be important for what comes next.
Right. Lead the way. What's section 7 about?
Section 7 is where we bring back those FOP sections and talk about regular ones.
Regular FOP sections. Okay. What makes them special?
They satisfy a certain condition that ensures their zero loci. You know, the points where they vanish are smooth manifolds.
So it's like we're adding an extra constraint to make sure everything stays nice and smooth.
Exactly. This regularity is super important because it allows us to apply all those resolution techniques we've been talking about effectively.
I see. It's all starting to come together now.
And this section goes into detail about the conditions for regularity and how they relate to those stabilizers of the orbifold.
Right. Those pesky stabilizers that tell us about the symmetries around singular points. It's all connected, huh?
It really is. And the coolest part is that they show how to use the F infinity ER algorithm and those smooth universal zero loci to resolve the singularities of the zero loci of regular FOP sections.
Wow. It sounds like they've covered all the bases. So where do we go from here?
Now things get even more abstract. We move into the realm of derived algebraic geometry with section 8, from derived orbifolds to orbifolds.
Oh, derived orbifolds. Now we're really getting into the deep end.
I know, right? They're basically sophisticated generalizations of orbifolds, capturing more information.
More information. Like what kind?
Think of it as adding an extra layer of detail, like infinitesimal information.
Infinitesimal. Okay, you're losing me a bit here. Can you give me an analogy or something?
How about this? Imagine you're looking at a curve. An ordinary orbifold would just tell you about the points on the curve, but a derived orbifold would also tell you about the tangent lines at each point.
Ah, so it's like knowing not just where you are, but also which direction you're facing.
Exactly. And this extra information is really important in a lot of contexts, especially when you're dealing with moduli spaces in symplectic topology.
Moduli spaces, those keep popping up.
They really do. And this section explains how the paper connects the Bordism theory of derived orbifolds to the underived orbifold Bordism we've been talking about.
So it's like building a bridge between the ordinary world of orbifolds and this more abstract world of derived orbifolds.
Exactly. And that bridge is essential for proving the paper's big splitting result, the one that links complex Bordism to the Bordism theory of complex derived orbifolds.
Ah, yes, the main attraction. So we're almost there.
Yeah.
What does the last section cover?
Section 9 is all about applications. This is where we see the paper's ideas put into action. They show how their techniques can be used to define those special Gromov-Witten invariants and study Hamiltonian fibrations over S2.
Sounds like the grand finale. Okay, so we reached the final section of this incredible paper, Section 9, Applications. It's time to see how all this theoretical machinery can be put to use.
It is. And the authors don't disappoint. They show how their methods can be applied to two really important areas, Gromov-Witten theory and Hamiltonian fibrations over S2.
Let's start with Gromov-Witten theory. I'm still trying to wrap my head around how this paper allows us to define those invariants in terms of complex cobordism.
Right. Remember how we talked about global Kuranishi charts?
Yeah, they're like convenient representations of moduli spaces, right?
Exactly. Well, the paper shows how we can apply all those singularity resolution techniques to these charts.
I see. So by smoothing out the charts, we can get a handle on the moduli spaces in a more refined way.
Precisely. And that leads to the definition of complex cobordism valued Gromov-Witten invariants for any closed symplectic manifold.
Wow, so we've gone from very limited cases to being able to do this for any closed symplectic manifold. That's a huge leap.
It is. It opens up a whole new world of possibilities for studying these manifolds.
Okay, so that's Gromov-Witten theory. What about Hamiltonian fibrations over S2? How do those fit into the picture?
Well, Hamiltonian fibrations over S2 are these fascinating geometric structures that capture the dynamics of Hamiltonian systems.
Right, we touched on that before. They're like maps from a space down to the two-sphere, but with some extra structure.
Exactly. And the paper shows how to construct stable, complex, derived orbifolds associated with these fibrations.
So again, we're connecting dynamics to the world of orbifolds.
Yes. And it goes even further, relating these derived orbifolds to moduli spaces of pseudo-holomorphic curves.
Moduli spaces, always topping up. It's amazing how interconnected all these concepts are.
I know. It's beautiful, isn't it? It really shows the power of abstract mathematics to reveal deep connections between seemingly different areas.
I couldn't agree more. So as we wrap up this deep dive into Bordism and resolution of singularities, what's the big takeaway you want our listeners to walk away with?
This paper is a true tour de force. It's full of innovative techniques, surprising connections, and powerful applications. It's going to have a major impact on multiple fields of mathematics for years to come.
I completely agree. It's been an amazing journey exploring this paper with you, and I have a feeling this is just the beginning. Who knows what other incredible mathematical discoveries are out there just waiting to be uncovered.
That's the beauty of mathematics, isn't it? There's always something new to explore.
Exactly. So to all our listeners out there, keep those minds curious and keep exploring the wonderful world of mathematics. Until next time, happy diving. Welcome to another deep dive. Today we're going to be talking about complex Bordism and its applications to equivariant stable harmotopy theory and symplectic topology. All from this paper right here, Bordism and Resolution of Singularities by Mohammed Abouzaid and Shaoyun.
It's going to be a wild ride. This paper goes through a lot of abstract mathematics, but it gives us a much deeper understanding of some very concrete geometric and topological objects.
So let's start with the basics. For anyone who's unfamiliar, can you give us a quick refresher on Bordism?
Sure. So imagine you have a bunch of manifolds, those spaces that look like Euclidean space locally. Well, we can group them together based on their boundaries. Two manifolds are considered bordant if together they form the boundary of a larger manifold. Like think about a cylinder. The two ends of the cylinder are circles, and those circles form its boundary. So those circles would be bordant.
Okay, so classifying manifolds based on their boundaries.
Gotcha.
And so this paper takes that idea and applies it to complex manifolds, leading to the concept of complex Bordism.
That's exactly it. And complex manifolds have a specific kind of geometric structure, and when you add that structure, it enriches the theory of Bordism in some really interesting ways.
I noticed the applications in this paper were very diverse. Like we're talking about connections to equivariant stable homotopy theory, Gromov-Witten theory, symplectic topology. It's a lot.
It is, and it's a testament to how interconnected mathematics really is. The authors did a good job of tying together concepts from many different fields to create something that is very insightful.
So let's dive into the first main point then, the connection to equivariant stable homotopy theory. This is where we start to see the power of complex Bordism in understanding spaces with symmetries.
Right, so equivariant mathematics is all about spaces that have some built-in symmetries, like rotations or reflections. Think about a sphere. You can rotate it all around and it still looks the same. Complex Bordism gives us some powerful tools to understand these symmetrical spaces in new ways.
And one of the key results here is Theorem 1.6. It kind of bridges the gap between what's called geometric Bordism and homotopical Bordism. Can you break that down for us?
Sure. So in geometric Bordism, you're dealing with spaces that you can physically glue together along their boundaries. But in homotopical Bordism, you're thinking about spaces that can be continuously deformed into each other. Think about that classic topology example of a coffee cup turning into a donut theorem. 1.6 connects these two worlds, so we can transfer insights from one to the other.
It's like a translation tool. You can move between these two different perspectives of Bordism.
Yeah, exactly. And one interesting thing about this theorem is that it connects to what is called the evenness conjecture for geometric Bordism. This conjecture says that certain Bordism groups are all made up of even numbers of elements. And Theorem 1.6 tells us that if this pattern breaks down in geometric Bordism, then it also breaks down in homotopical Bordism.
Wow. So the fate of this conjecture in one area of Bordism is tied to another area. That's a pretty big connection.
It really shows the interplay between geometry and topology. And another interesting tool the authors use is the localization sequence. This sequence relates the Bordism of a space to the Bordism of its fixed point set under a group action.
So you're focusing on the points that stay fixed under these symmetries and see how they contribute to the structure.
Exactly. And this gives us even more insight into the relationship between complex Bordism and homotopical Bordism.
Okay, so let's move on to the second main point. This one takes us to geometry and Gromov-Witten theory. Now, this is where it starts to get really interesting.
Yeah, so Gromov-Witten theory is all about counting certain geometric objects, like curves on a surface. Like, say you have a sphere and you want to count how many different ways you can draw a circle on it. Gromov-Witten invariants help us do just that.
Okay, so you're counting curves on shapes. Sounds simple enough, but I'm sure it's actually very complicated.
Oh, it definitely gets complicated. Traditionally, these Gromov-Witten invariants are calculated using something called virtual fundamental classes, which are these abstract algebraic objects. But this paper gives us a totally new way to define them using complex Bordism.
So complex Bordism is offering a new way to think about this important concept.
Exactly. Theorem 1.13 is a central result in this section, and it offers a more geometric way to understand these Gromov-Witten invariants. Traditionally, you would be working with these abstract virtual fundamental classes, which are pretty difficult to understand. But now we're talking about actual geometric objects, manifolds, that represent these invariants.
So instead of manipulating abstract algebraic objects, you're dealing with something visual, something concrete.
You got it. And we can take these manifolds and use complex Bordism to analyze their properties and figure out more about these Gromov-Witten invariants they represent.
That's really cool. It's like you're translating a problem from a language you don't really understand to one that is easier to grasp.
You could say that. And it's all thanks to the power of complex Bordism. This approach could lead to a lot more research in Gromov-Witten theory.
So this paper isn't just about using complex Bordism, it's about creating new tools and techniques. And that brings us to the concept of resolution of singularities, which seems like it's really important for the authors.
It is resolution of singularities is like a main theme of this paper. You can think of singularities as like rough spots on a geometric object, places where it's not smooth, like a sharp corner on a cube or the tip of a cone.
So it's like an imperfection in an otherwise smooth surface. And I'm guessing mathematicians aren't big fans of those.
You got it. Singularities make a space harder to work with mathematically. They can throw off our calculations and make it harder to understand the underlying geometric structure.
And that's where resolution of singularities comes in. We smooth out those rough spots.
Exactly. It's a bunch of techniques for turning a space with singularities into a smooth, well-behaved space. But we still want to keep the important information about it.
It's like a mathematical makeover. You're giving these geometric objects a smoother look.
That's a great way to put it. And in this paper, the authors want to use this technique to work with something called a normally complex orbifold.
Okay, before we get into that, can you tell us what an orbifold is? They sound kind of mysterious.
So an orbifold is almost a manifold. It might have a few singularities, but we can still do geometry on it. And a normally complex orbifold is an orbifold with a normal complex structure, which is a specific kind of geometric structure that makes it work well with algebraic techniques.
So it's like a manifold, but with a few quirks. But it comes with a set of tools that we can use to analyze it.
Exactly. And one of the important steps the authors use in this whole process is something called abelianization.
Abelianization, what is that?
Well, it's a process where you do a series of transformations called blow-ups. A blow-up is kind of like zooming in on a singularity and replacing it with a smoother space. When we do a bunch of blow-ups in the right way, we can transform the orbifold so that its stabilizer groups become abelian. That means that the symmetries of the orbifold at each point can be described as combinations of simpler independent transformations.
So instead of having these complicated intertwined symmetries, we're breaking them down into more manageable pieces.
Exactly. And the authors show us exactly how to do this in a way that makes sense. They use this invariant called the codimension of stackiness to guide the blowups. So they're always targeting the points that are the most singular, and they reduce the complexity of the orbifold in a step-by-step way.
So it's a strategic plan for smoothing things out.
Exactly. And they point out that it's important to do all this functorially, which means that the blowups need to work with any maps or relationships between the orbifolds we're thinking about. This makes sure that we keep all the mathematical structure during the process.
So it's like doing surgery. You don't want to damage anything important.
Exactly. And the authors mention that there are other ways to do this abelianization, like stuff based on work by Batarev or Bierstone and Millman, but those ways can be more complex or they might not be as geometrically clear as the approach in this paper.
So the method in the paper is like a specialized tool for taking care of those singularities.
Exactly. And this sets us up for the next step in the process, which is deorbification.
Deorbification. That sounds pretty intense. So how do we do that?
The idea here is to take our abelianized orbifold, which still has those singularities, and turn it into a smooth manifold. No more trouble from singularities.
Right.
And the authors give us a 4-step plan to make it happen.
It's like a 4-stage rocket launch to a world without singularities. So tell me about these steps.
Each step uses a carefully chosen blowup to target specific singularities and smooth out the orbifold. In the first step, we look for the place where a certain invariant hits its maximum value. This invariant is a combination of something called the independence index, the toroidal index, and the divisorial type. And then we do a blowup along that place, targeting the most singular points.
And so you're picking the spot for your blowup based on this invariant. It's like you're launching a missile at those singularities.
Exactly. Now, step 2 focuses on reducing the toroidal index. That basically measures how twisted the orbifold is around a singular point. We do a blow-up where this index is the highest, and that simplifies the orbifold even more.
You're untwisting those mathematical knots. What about step 3?
Okay, so in step 3, we look at the divisorial index. This tells us how the singularities are affected by certain subspaces called divisors. And again, we do a blow-up where the divisorial index is highest, and that smooths things out even further.
So we're getting rid of the influence of those divisors. And finally, step 4.
The last step reduces the independence index.
Yeah.
That measures how complicated the stabilizer groups are at each point. By doing a blow-up where the independence index is highest, we finally get a smooth manifold, a space with no singularities.
That's incredible. So we started with this orbifold that could have been really messy, and now we have a nice, smooth manifold.
Yeah. And the best part is that this whole thing, from abelianization to deorbification, is designed to be functorial. That means our new smooth manifold keeps all the essential information from the original orbifold. We haven't lost anything important.
So you've given the space a makeover, but it's still the same space at its core.
Exactly. And this brings us to the question of how this whole process of resolution fits into the big picture of Bordism.
Okay, so we spent a lot of time talking about how to smooth out these singularities. But how did this all connect back to Bordism? It seems like we went off on a bit of a tangent.
We haven't, actually. One of the cool things about this paper is that they show how you can do this whole resolution process, and it's still compatible with the idea of Bordism.
So you're not just smoothing out individual spaces. You're smoothing out entire families of spaces that are connected through Bordism.
Yeah, exactly. The authors can take a whole Bordism class of orbifolds, so that's a collection of orbifolds that are all bordant to each other, and they can turn it into a Bordism class of smooth manifolds, and the Bordism relations still hold.
Wow, so you're basically smoothing out the entire Bordism world. You're taking something that could be rough and bumpy and making it nice and smooth.
Exactly. And the way they do this is by using what they call functorial embedded resolution of singularities applied to universal zero loci. Those might sound like complicated terms, but they're the key to going from these abstract derived orbifolds to the more concrete, smooth manifolds.
Okay, break those terms down for me. What are universal zero loci, and what do they have to do with all this?
Okay, so imagine you have a space of polynomial maps. You know, those functions with multiple variables that are sums of powers of those variables. Well, the universal zero locus is the set of all the points in this space where a certain polynomial map is equal to 0. It basically captures the solutions to a whole bunch of polynomial equations.
So it's like a blueprint for the solutions to these equations. Sounds useful. But where does the functorial embedded resolution of singularities fit in?
Well, the authors use a big result from Abramovich, Temkin, and Vludarczyk. They came up with a way to systematically resolve the singularities of these universal zero loci. And they did it in a way that's functorial, which means we don't mess up any of the relationships between the spaces we're working with.
So you're giving these universal zero loci a makeover without changing their structure. But why are these universal zero loci important for understanding derived orbifolds?
The key idea is that derived orbifolds can be modeled locally as quotients of these universal zero loci by the action of a finite group.
So you're taking these universal zero loci and you're adding a layer of symmetry to them by looking at their quotients under these group actions.
Exactly. And when you apply this functorial resolution of singularities to these quotients, you end up with smooth manifolds that capture the important information from the original derived orbifolds.
It's like you're taking those abstract derived orbifolds and distilling them into smooth manifolds that are easier to work with.
That's it. And to represent the derived orbifold globally, the authors use something called smooth bundles of algebraic varieties. You can think of a bundle as a way to glue together a bunch of spaces over another space. The spaces we glue together are called fibers, and the space we glue them to is the base space. In this case, the fibers are algebraic varieties, which are objects defined by solutions to polynomial equations.
So you're taking these bundles of algebraic varieties and smoothing them out.
Exactly. And the authors show that we can use these smooth bundles to represent a derived orbifold, even if the orbifold itself has singularities.
It's like you're building a smooth model out of pieces that might have been singular.
You got it. And the important thing is that the authors build these bundles very carefully. They make sure to keep all the important topological and geometric properties of the derived orbifold.
So it's not just any bundle. It's specifically designed to accurately represent the derived orbifold.
Right. And that brings us to the applications of all this, like in Gromov-Witten theory and Hamiltonian fibrations.
Okay, so back to those examples. How do these abstract ideas connect to actual geometry and topology?
Well, one thing is that the authors have developed a new method for defining and computing Gromov-Witten invariants. Remember, those invariants help us count geometric objects. Well, now we can understand them in a more geometric way using actual visualizable objects.
So we're moving from abstract calculations to geometric insights. What about those Hamiltonian fibrations, those bundles with the energy component?
Yeah, so the authors use their results to study the topology of those vibrations. They resolve the singularities of certain derived orbifolds that are related to those vibrations, and that gives us new ways to explore those objects.
It's amazing how all these different ideas connect together and shed light on different parts of math.
It really is. It shows how interconnected everything is.
Well, I think that about wraps up our deep dive into Bordism and resolution of singularities. It's been great to explore these concepts with you.
I've enjoyed it too. And to everyone listening, thank you for joining us. Keep exploring and never stop learning.